So now I have shared my screen. That is being shared now, and I hope you can all view my screen.
Yes, sir.
Yes, sir.
Okay. So during the last class, that was where we stopped in the last class, and we actually solved some problems that was pertaining to circular motion. And under the circular motion, the question we solved in the last class was this, that you have a 150-gram ball at the end of a string which was being revolved uniformly in an horizontal circle of radius 0.6 meters. The ball makes 2 revolutions in a second. What is its centripetal acceleration? So in the last class, we discussed about when you have a circular motion of this nature, maybe you have an object performing that, something keeps the object moving in this circular path, and what does that is what we refer to as the centripetal force. Is referred to as the centripetal force. And associated with the force as a result of the Newton's second law, where we have F is equal to ma, must therefore be an acceleration. So the acceleration, centripetal acceleration, which is directed towards the center of the circle, keeps the object moving in the circular path. The moment the centripetal force is not there, what happens? This thing will not move in a circular path, but moves away from the circular path. And what makes it to move away when the centripetal force is not there again is what is called the centrifugal force. That does that. So the centripetal force is what keeps this object moving in the circular path without dissuading from the circular path. Now with this now, if you look at the solution we have here now, we asked to calculate the centripetal acceleration. But for us to calculate acceleration, we all know from basic Newtonian mechanics that acceleration is equal to what? How do we calculate that? Acceleration is always what? That's the speed divided by what? By time. That is what acceleration is. Acceleration is the velocity divided by the time. While calculating the velocity, that is the displacement divided by what? Divided by time. Such that if you differentiate twice the displacement, you surely have the acceleration. So in this case, for us to determine the acceleration, we need to first of all find the velocity. And how do we find the velocity? It is displacement over time. So what is the displacement now? That is the circular part. That's a circumference of a circle. So in order for us to determine that, that will give us 2 pi what? 2 pi r divided by the time it takes. So the time to complete one cycle is what is called the period. And the period we have here is 0.5. How did we get 0.5? It's from these 2 revolutions. 2 revolutions stands for frequency. That means we have 2 hertz. And in order to calculate frequency, frequency is given as what? The reciprocal of the period. So from here now, the period will always be equal to what? Reciprocal of what? Of frequency. And what is the frequency here? The frequency here is 2. And that is the reason why we have 1 divided by what? 1 divided by 2, which gives us 0.5 seconds. And that's why we have 0.5 here as the period. We know the pi, we know 2 is a constant term, and the radius The radius given to us here is 0.6 meters. So when we solve for this, we add the velocity. So in order to calculate the velocity under circular motion, is usually given as what? V squared divided by what? Divided by R. And that is what has been done here. So we're able to calculate our centripetal acceleration. So we've been able to calculate what the centripetal acceleration looks like. And that is what we have here now. We have the centripetal acceleration. So any question?
No, sir.
Okay. So we then move on to another simple question that we can solve together here. This is pertaining to the celestial bodies. That is, you have the moon and you have the earth. Now, the moon's nearly circular orbit about the earth has a radius of about 384 kilometers. So, which means you have the earth and you have the moon moving around the earth. Or the earth, you see the earth is rotating. And that is what gives the light and the day. So the sun and the moon are around this. So it depends on which place of the earth is directly in contact with the moon. Those places we experience night. Those ones in directly in contact with the sun, we experience the day. Now, at the period T, which is 273, determine the acceleration of the moon towards the earth. The acceleration of the moon towards the earth. So that is more of the centripetal acceleration. So you have acceleration of the moon towards the earth. Now, in order for us to solve this problem, we've been given the radius, which is 384. This is what we have here. Is the radius of its circular path. So that's the radius of the earth. The radius of the circular path is given here, and we have it in meters. That's the radius. So the time required for one complete orbit is 27.3 days, like we have here. So the speed of the moon in its orbit about the earth is still given as what we used earlier. V is equal to 2 pi r divided by t. So from here, the period t in seconds is given as this because it's in days. So we have to convert to seconds. And that is what had been done here, which gave us 2.36 seconds. So therefore, in order for us to calculate the acceleration, what has been done here now, acceleration is given as v squared divided by r. But mind you, our v is equal to 2 pi r over t. So if you substitute in that one, that will be 2 pi r squared over what? That will be over t squared multiplied by r. So if you break this down further, you have 4 pi r squared divided by what? T squared r. So if you put in the necessary parameter, which we know the period, we know the radius, if you substitute them into this, it gives us this, meters per second square. That's the acceleration. Meters per second square. That is what you have. So any question or query? Any question or query? I hope it's well understood.
Yes, sir.
Okay, thank you. Yes, what do you want to say? Okay, so
Sir, please slide.
huh?
Sir, please slide for the topic, for the note.
There is what?
Sir, please, for the slide.
You
I'm
are
not getting the slide.
Try to understand first, Bobo.
understand what is being taught before asking for slide. Asking for slide. What do you want to do with the slide? Instead of you to pay attention and go and look for textbook to study. Slides are to teach. They are meant to be taught. It's prepared by the lecturer to be used in teaching. You're asking for slide. I'm asking you, do you have any question? You're asking me for slide. Is that a question?
Sir, excuse me, sir.
Yes.
I have a question, sir.
So what's your question?
Yeah, sorry, sir. Please, the answer to the first question, sir. I missed that last part before you switch the slide, sir.
What did I say?
Can I just get the answer to the last slide?
This is it. I'll share the recording. It will send to be subbed in, and it's going to share the recordings with you. So I have opened it. This is it.
Hello, sir.
Yes.
So the second slide, where you solved the second question, sir.
Okay.
Sir, sorry, I missed a particular point there because, sorry, sir, can you go back to the second slide?
This one.
Yes, sir. Thank you very much, sir. So, sir, in the solving, you wrote there that the A is equal to V square over R, then equals to this 2 pi R square.
For circular motion.
Yes, sir, over T square R. So I didn't get the T square because it was only period that was given to we were not made to know in the question, sir, that it was.
Remember that V is equal to 2 pi R divided by T. So in
Yes,
place
sir.
of V square now, if you put 2R over T there, you know this will be squared.
Okay.
2 pi R also will be squared. So it will give you this.
Yes, sir. Okay,
So
sir.
you can then slot in the radius given to you as well as the period which you calculated.
Okay,
So
sir.
your answer will be this.
Okay, sir.
I hope it is clear. Okay.
So I have a question.
So what's your question?
After getting your acceleration of the moon, you wrote we can write this acceleration in terms of G equal to. I don't understand that part.
Yes, if you decide to write the acceleration in terms of G, that means if you divide by G what you got here, if you divide by G, which is 9.8, you can write it in terms of this. You know, you are dealing with celestial body, the moon and the earth.
Yes, sir.
And the acceleration to the gravity is present between them. There's that force of gravity between them. That's why we say you can also write it in terms of G. So we divide by G. Is it clear?
Okay, sir. Yes, sir.
Is it clear?
Yes, sir. Thank you, sir.
Okay. So let us now move on to the next topic, which is rotational motion. Where's the slide?
Sir.
Yes, I'm with you.
Some people are yet to be accepted to the class. So.
It's filled up already. I have 300. So it cannot take more than 300.
I'm seeing 193 here.
I am the host. I am the host. So it has 300 here.
Sorry, please, you skip the gravitational part.
Yes, I skipped it because it's not time to teach it. It's the last part that I'm going to teach you. Is that clear?
Sir, thank you, sir.
So some set of lecturers will also take you for another stuff, so of which then I will take you again. It's the last part. It's not time to teach you. That was why I skipped it. So what I'm to teach now is rotational motion. I hope it's clear. Okay.
Yes, sir.
Please, this person should unmute. Who is this?
Don't worry. I will mute everyone now. I will do that. So now, What we haven't moved from the circular motion now, we will move on to rotational motion. They are almost similar, circular, rotational. And if you remember, for the circular, basic things, we discussed about centripetal force, centripetal acceleration, which led us to velocity. Velocity under this gives us 2 pi r divided by the period taken. And we all know what the period is equal to 1 divided by what? The frequency. Why the acceleration is given as what? V squared divided by what? Divided by our r. That is what we have here. So from here, we then move on to rotational. So under rotational motion, we will discuss about angular quantities. We will discuss about constant angular acceleration. Then we'll also discuss about rolling motion. We'll discuss about the torque. We'll discuss about rotational dynamics, torque rotational inertia. Then we'll solve some problems. And we'll also discuss about rotational kinetic energy, angular momentum and its conservation, the vector notation of angular quantities. Now, we'll begin. In purely rotational motion, all points on the object move in circles around the axis of rotation. This point O is the axis of rotation. So all points on the object moves in a circle, and that's why we have this. So the radius of the circle is given as r. So all points on the straight line drawn through the axis move through the same angle. So which means if you move from here to here, even from here to here, even from here to here, they will surely cover the same angle. And that angle being covered is what is called, is referred to as theta. And that's what you have here. So basically the angle covered, just like you have the hands of the clock moving, the angle covered is given as what? As theta. And that theta is equal to what? What is covered here, like a displacement L, divided by the radius of the path taken. So this L is the arc. This is an arc of a circle. So which means in order to get that theta, it will be the arc divided by the radius. So that is what we have. And that theta is measured in what? Is measured in radians. So there's a correlation between angles in degrees and angles in radians. Well, we see that as we progress. Now, this is a question. A particular bird's eye can just distinguish objects that subtend an angle no smaller than about this radian. That's the angle subtended by the object, but the eye can see it if it is within this. So how many degrees is this? So in order to do that, we need to convert these 3 times 10 raised to the power minus 4 radians to degrees. So in order to do that, we all know that 2 pi radian is equal to 2 pi radian is equal to 360 degrees. Therefore, 3 times 10 raised to the power minus 4 radian will be what? So that will give us 3 times 10 raised to the power 4 divided by 2 pi radian multiplied by 360. So doing that conversion, we will have this 0.017. So that's the conversion. Now, the second question, how small an object can the bird just distinguish when flying at a height of 100 meters? When flying at a height of 100 meters. How small an object can the bird just distinguish? So we all knew earlier that our theta is equal to what? R divided by L. So from here now, in order for us to, which is, the question says, okay, flying at a height of 100 meters. So if it's flying at a height of 100 meters, we already know that our R, because we have the surface of the earth now. So we have a bird that is flying at 100 meters. So you have the whole of this as 100 meters. That is the radius. So having known the radius now, which is 100, we then multiply by this in rad. 3 times 10 raised to power minus 4. So since R is this and our theta is this, so we can find L from what we did here. Theta is equal to what? L divided by R. Theta is L divided by R. So in order for us to get our L here will be equal to what? R multiplied by theta. Because that L we have just found is how small an object can the bird just distinguish. So if the bird is here and that is on the surface of the earth, it's on the surface of the earth here. So if the bird is here, so how can it detect it? So that is what we are trying to calculate. And it is 3 cm. That is the size of the object. The size of the object is 3 cm. So if it is here, this is at 100. This is the radius which we are given. So from O to P, we have it at 100. So theta is equal to L divided by R. We are finding the L. L is theta R. Our theta, which we must know, is in radian that we know. Then we have the radius. So if an object is here, how will the bird see the object? So that is what we have just been able to calculate, which is given as 3 cm. Any question?
No, sir.
So take note of this formula as well. Now, we have a situation where there's a change. Maybe there's a displacement from where the object was before to this place. Initially, it moved from here to here and from here to here. So which means instead of having normal displacement for mechanics, here we now have what is referred to as angular displacement. So angular displacement will be what? Theta 2 minus what? Theta 1. Angular displacement will be theta 2 minus what? Minus theta 1. So the average angular velocity is defined as total angular displacement because we are trying to find velocity. And velocity is distance over what? Time. So this will now be, velocity is displacement divided by time. So displacement we have here, this is this divided by time. But if we are talking about instantaneous angular velocity, then there must be a limitation. Instantaneous angular velocity. So any question?
No, sir.
So what we are dealing with now is a rotational motion, which deals with the angular displacement. Now we have the acceleration. Since we had said that the angular velocity omega, Then we can then have the angular acceleration. We have the angular acceleration. We have the angular acceleration. So that is our alpha. So in order to get acceleration, it will be changing speed divided by what? Change in velocity divided by time. And since change in angular velocity is given as omega, so this is the final velocity, this is the initial. So we can get that from here. So now, the acceleration instantaneous will be given as limit of this with respect to velocity divided by the time. So any question with respect to this? Any question?
No, sir.
Okay, thank you.
No, sir.
Okay. So now we then have for every point on a rotating body as an angular velocity and a linear velocity. So for every body rotating, it will have two components, the angular and the linear. But there's a relationship between the angular velocity and the linear velocity, and this is the relationship between them. Where this is the linear velocity, and this is what? And that's the angular velocity. So what is common to both is the radius. So take note, we have been able to do two things. One is the angular displacement, which is given as theta. And theta is equal to what? We have angular velocity. Angular velocity will be given as the theta divided by this. Change in the angular displacement divided by time. And to get the alpha, which is the acceleration, is equal to what? Change in velocity divided by what? Divided by time. And you also take note of V is equal to what? RW. So that is what you have here. So from here now, we can then proceed so here, in order to find the tangential angular velocity, it is this. That's the linear divided by this. And for V, we knew earlier that V is equal to RW. And this does not change. That's why it's a constant term. So what is changing is now the omega and the time. The omega and the time. So such that if you now come to the acceleration, we knew from the circular motion that acceleration is always V squared divided by what? R. But from here, since V is equal to RW, so we can then have that A so that is what we have. A will then be equal to this square divided by what? Divided by R. So we can then have omega square, R square divided by R. This crosses this. We then have A to be equal to omega square R. It will be omega square R divided by R. A from there is omega square R divided by, what did I do? This cancels this. Okay, it's omega square R because this would have cancelled this. So A is equal to omega square R. So that is what we have. And that is what is here. So I hope it is clear.
So sorry, please, can you go over it again? This page.
Now, I said earlier that angular velocity, which is omega, is giving us the displacement in the angle divided by time. When that occurs, we also have the angular acceleration. For acceleration, the change in the angular velocity divided by time. I hope it's clear up to that point.
Yes, sir.
Now, there's always a relationship between the angular velocity and the linear velocity. And that relationship between them is that V is equal to what? R omega. So from here, it now makes it very easy when we have the acceleration to be V squared divided by R. So from here now, since you know that your acceleration is V squared divided by R, you can then bring in what you have here, that V is equal to what? R omega. You then have R omega square divided by R. So which is R square omega square divided by R. This crosses this. So your A will be equal to omega square R. And that is what we have here.
Okay, sir. Thank you, sir.
Okay, thank you. Now, some of the relationship between the angular, the rotational, and the linear. Because for the linear, we have the X, while for rotational, we call that theta. Linear, we have the, while for this, we have omega. Here we have A tan theta, but yeah. Okay, you have the velocity V, omega is this for rotational. Then you have the linear A tan, which is called acceleration, and you have A tan is equal to what? Alpha. You have the R alpha. That is what you have for the tangential component. So is it clear? I hope it is clear.
Yes, sir. It is clear.
So now we have an example. A carousel. Carousel is what is used in the airport. When you arrive at the airport, you see your baggages moving around it. So that's what is called the carousel. It's initially at rest. At t is equal to 0, it is given a constant angular acceleration. It is having an angular acceleration, which means you have your alpha given alpha to be 0.06 rad per second square, which increases its angular velocity for 8 seconds. It increases angular velocity for 8 seconds. That means change in time. So that is what you have. You have 8 seconds. So at t is equal to 8 seconds, determine the following quantities. A, the angular velocity of the carousel. So how do you calculate the angular velocity? Angular velocity is equal to what? This displacement divided by what? Time. So from here now, it's quite easier for us to move on. So to calculate the, so we have the acceleration. But mind you, remember that acceleration is equal to what? Omega square what? R. But here, we can calculate our T. This is our acceleration. So acceleration can also be written as this. So solving for Now, if you are trying to solve for the angular acceleration to be angular velocity divided by change in time.
Yes.
Now, so from here, we know the acceleration and we know the time change. So if we substitute this one into this, we have this. So which means we will have, if we cross multiply here, we will have omega 2 minus omega 1 equals to alpha. So that is what we will have from there. So we can then have omega 2 minus omega 1 divided by change in time. So what is our omega 2, omega 1? So the omega 1 is 0 because it was initially at rest before it starts to move. So that is what has been done here. And you have the alpha, that's the acceleration you got. That's the acceleration you got. That's the acceleration that was derived. So from there, then we can then substitute in the acceleration here, which is this, and the change in time, which is this. So we can have the omega 2 after it is in motion for that 8 seconds. So our omega 2 is this. That's our omega 2. That's the angular velocity after it has moved. And the angular velocity of the carousel. Yes. So this is what we have. So any question? Any question?
No, sir. No, sir. No question.
Okay. So the next problem is that we have to find the linear velocity of a child located 2.5 meters from the center point of the carousel. So a child with a linear velocity, you have to calculate the linear velocity of the child. And if you remember, between the angular velocity and the linear velocity, the relationship between them is what? Is this. So you already know the angular velocity and you know the radius. Was the radius given?
Radius.
If the radius is not given, but we know this, angular acceleration. So from what we have here now, acceleration is what? Radius multiplied by tangential acceleration is this. So can we see this now? Acceleration is omega squared and r. So if we go back to the question, we know our r because it was located at 2.5. So the linear velocity of the child located 2.5 meters from the center. From the center. So that means our r is what? Is 2.5. So the time is this. So to calculate the linear velocity, this is the relationship between them. V is equal to omega r. Radius is this, and our omega is 0.48 from here. What we derive from here. So we've been able to get the linear velocity. So any question? Any question? So the linear velocity and the angular velocity are related by V is equal to R omega. Now, in order to calculate the frequency, if you remember from our oscillations, omega is equal to what? 2 pi what? 2 pi f. So frequency is what? Omega angular velocity divided by what? 2 pi. Also, calculating the period is 1 divided by f by the frequency. So I hope it is clear.
Yes, sir.
Okay. So from here now, we now see this standard table to compare between linear motion and angular motion. So that is under the Newton's laws of motion. Under the Newton's laws of motion, we have this operating there, we have this, we also have this. This is average velocity. This is average angular velocity. That's average angular velocity. But I hope we all remember these equations, these three. So in place of the velocity now, you use omega. Initial velocity, you use omega naught. Acceleration, you use alpha. So the same thing. So when you are dealing with angular motion, you represent them with this. You represent them with that. So now, having understood this, it makes it very easy. Just like we're solving problems using this under the classical, under the Newton's motion, equation of motion. We'll also use this for angular motion as well. Now, I hope you don't have questions under angular motion and rotation. Hope you don't have questions.
No, sir.
Okay. So we then move on to torque. What do you refer to as torque? What is this? As I'm muting them. So what is a torque? To make an object to start rotating, a force is always required. So the position and direction So now, if you have a torque literally, you can refer to it as a force. Those in engineering and co, you see them, what is the torque on the object? So that means the force. So to make an object to start to rotate, maybe about a fixed point. For example, now, if you have the tap that brings out water, usually you have a control attached to it. Having this control, if you move this control now, if you create a force in this direction, if you move it this way, you find out that it moves this way about a fixed point. If you want to lock it again, you provide another force in this direction. It moves this way about a fixed point and is locked. So the position and the direction of the force, it matters as well. So the perpendicular distance from the axis of rotation to the line along which the force acts is called a lever arm. the perpendicular distance from the axis of rotation. This is the axis of rotation. So the perpendicular distance this way, rotation to the line along which the force acts, is called a lever arm. That's why you can refer to the lever of the tap, you can refer to it as a lever arm. So you apply a force this way, it moves it this way to open. If you apply it in the other direction, it closes it, but about a fixed point. So that's basically what we have. Now you can see the wrench. This is a wrench used by plumbers, used to tie this joint together. So a long lever arm is very helpful in rotating objects. This is a wheel spanner, trying to remove the knot of a tire, or you are trying to tie the knot properly. So this is also a lever arm. This is a fixed point, not moving, but this is the lever. So a torque is being provided by this hand in order to actually lock up that joint. Here, the lever arm for FA, force FA, is the distance from the knob to the hinge. This is the hinge. That is the hinge. So the lever arm for FD, this is FD. This is not doing anything. For this force, it is parallel to that point. So what we have here is 0. And the lever arm for FC is as shown below. FC is perpendicular. And that's why we have something this way to the radius that will be created. RC. So the distance from here to here. So any question? Any question?
No, sir.
No question, sir.
So an example is if you have this and you apply a force F here, this is a fixed point. There's also another force F1, F2. So whichever is heavier, it tilts towards that side. If the F1 is heavier, it tilts towards that side and it comes down this way. So that is what we have here.
Okay, sir.
So do you have a question?
No, sir.
Okay. So now we then move on to the arm. If you are using your arm to pick up something, maybe mass, a mass of, let's say, 500 grams. So you can see the force is perpendicular to the point of rotation, which lies along this way. So the load is here. So the torque is always, what's the formula for torque? Torque is perpendicular distance multiplied by what? The force exerted about that fixed point. So if it is at an angle, this is what we have. Angle of 60, angle of 30. So from here, it depends on what you are trying to do. But the force, because it comes from the biceps here, for you to be able to lift the mass that is here. That's why you see it in that direction. But it's perpendicular to, you can see the force and the perpendicular distance to that force. So that is the formula for to find torque. Now torque and a rotational body. So from here, in order to calculate the summation of the torque, because this is a circular part, you will definitely have different torque at different points. That's why we are summing them up. We are summing them up. So if it's rotational, this M is constant, but the acceleration is changing, angular acceleration at different points. So because F is equal to what? MA. But if you are having MA, that is M times lambda, and R is the perpendicular distance, which is squared. So that is what you have there. Any question? Any question?
Sir, can you please go through it
Over
again?
it again.
Sir, can you please
Yeah,
go over it again?
because it is a rotational motion, rotational dynamics, just like it is explained here. The torque cannot just be the perpendicular distance multiplied by the force about the fixed point. For rotational, it will be moving from here to here to here to here to here. That's why we have summation of the torque. And since we know it is this, so we then have summation of torque, which will now be what? F is what? MA, mass times acceleration. And under rotational, it will also be summation of what? M multiplied by angular acceleration. Then you then have this distance. And that will be what? R square. The distance will be R square. And that is what we have just done here. Multiplying force by perpendicular distance. And that's what we have here. So I hope it is clear.
Yes, sir. Thank you, sir.
Yes, sir.
Okay.
So I have a question.
So what's your question?
Sorry, I don't seem to understand the first line. After that, F equals to MA.
After F is equal to MA, because you are multiplying the force by the perpendicular distance, that is the formula for torque. But under angular, whatever, angular motion or rotational motion, you also have, instead of A, you have angular acceleration. Your mass stays. But to calculate your distance, you know, definitely, it's like moving from covering something like a circle. When it moves around, that's the distance it's going to cover. And you know, in order for you to discuss about the area that is covered, area of a circle is always what? By R square. And that is where this R square is coming from. So the area that is swept by this. So that is where this is coming from. So you then put this with the M lambda, and you can calculate the torque, which is the perpendicular distance and force. Where the force is mass times acceleration. Yes?
Sir, please, why is the lambda or acceleration outside the bracket? I thought you said it was changing. Why are we not doing summation of it here?
Yes, it is changing, because that is what eventually will determine the torque from one side to the other. If you remember when I was talking about a vehicle moving around when they are doing a vehicle, a car racing, you know, when it gets to some angle, it has to slow down. If you have an object moving, in order not to skid off, so that centrifugal force will not take it this way, for it to maintain that, it has to slow down. That's why when you are negotiating a roundabout with a vehicle, you don't negotiate a roundabout with a speed. At some point, you need to slow down. And once the velocity reduces, definitely the acceleration also increases. Do you understand that?
Yeah,
But the
yes,
mass of the object will not change. Also, the radius covered, the distance covered will not change. That's why they are in the bracket. Do you understand that?
Yes, sir.
Huh?
Sir, yes, sir. Yes, sir.
Okay. So this is rotational inertia. Do I bother you with this? No. Let me bother you with all this. No. So now, in order to draw this, all you need to do is just to have a sketch. If your force acts this way, just like I informed you about the tap is fixed. This is the lever. And that's the perpendicular distance R. So if a force is applied this way, you see this lever moving this way. If it's applied the other way, you have the lever moving that way. It is only when it's point, the lever is point, that you can have it observing this. So you find the axis of rotation, then calculate the torque around it. So we've known that now the torque is given as this. And when you have the torque given as this, you have it as the F multiplied by the perpendicular distance, R. But this distance is given as what? R squared. Why this is given as what? Mass multiplied by the angular acceleration. So that is what you have. And that was what gave you this. That was what gave you what you have here. The summation of the torque. So the torque varies from one place to the other, depending on the kind of acceleration given to it. So do I bother you with all this? No. No. Let me just see. So in summary, angles are measured in what? They are measured in radians. They are measured in radians. So a whole circle is equal to what? 2 pi radian. And that was why I said 2 pi radian is equal to what? 360 degrees. So if you have anything in radian and you have to convert, then it's easier for you to convert. So angular velocity is the rate of change of what? Angular position. Angular velocity is the rate of change of angular position. And that's why we have this. So the change in angular velocity will be the change in angular displacement divided by what? By time. That is what we have there. While angular acceleration, our angular acceleration, change in this will be change in angular velocity with respect to what? Respect to time. So the angular velocity and angular acceleration can be related to the linear velocity and acceleration. So the linear velocity related to it is this. This is the linear velocity, and this is the angular velocity with respect to the radius. So the frequency, just like we said, that is full revolution. So the frequency is related to the period by this. It's related to it by this. This is what you have. So the equations for rotational motion with constant angular acceleration have the same form as those for linear motion. They have the same for linear motion, and that was what I showed you the relationship earlier. I gave you this relationship earlier, which I showed you that this. Can you see? For linear motion and angular motion, they are related. Where you have the speed, you relate with omega. Where you have acceleration, you replace with alpha. And this is what you have. These are average velocity and for the angular, and this is for the linear. That's what you have there. So going by that, So the angular acceleration is proportional to the torque. Angular acceleration is proportional to the torque. And that was what we had here. Where you add the summation of the torque is given, and you know torque is force times perpendicular distance.
Yes.
Where you add summation of what? Summation of the mass. And you add the distance covered. And you add
acceleration angular.
Yeah. So that is what you have. So an object that is rotating has rotational kinetic energy. So if it is translating as well, the translational kinetic energy must be added to the rotational to find the total kinetic energy. So in order for us to find total kinetic energy, we will sum up total rotational. You have kinetic energy of rotational added to the kinetic energy of translational. So when you talk about translational, maybe you have an object here. If it moves from year to year, that's translational. Like the tire of a car, if the vehicle is moving, it's observing two forms of motion, both translational at the same time rotational. So that is what is happening. An example of what we have here is the tire of a vehicle. If the vehicle is moving, it's performing both translational and rotational motion together. So in order to get the total kinetic energy for that kind, you sum up both the rotational and the translational together. So if the net torque on an object is 0, its angular momentum does not what? Does not change. Take note of that. If the net torque on an object is 0, that's the total force on an object is 0. So the angular momentum does not change as well. So that is that. So that is where we'll stop for today.
How are you?
We'll stop here for today. And
All right,
Thank you, sir.
the class will
With me.
next
I
week.
have a question, sir.
Thank you,
What's your
sir.
question?
Thank you.
What's your question?
So what's the difference between torque and moment of a force?
The torque and the moment of a force is the same thing. Torque and moment of a force is the same thing. If you remember moment of a force, it's always the product of the force.
Line of action.
But the problem is that for the torque also handles rotational motion. Torque also handles rotational motion. So it makes it clearer when you talk about torque. Torque is more professional. So for those in engineering, you will find out that most often they make use of torque. Torque. So it's more conventional than talking about moment of a force. So I hope it is clear. I hope it is clear.
Yes, sir. Yes, sir. Thank you.
Yes, sir.
So thanks for the attention. We will continue next week. So thanks for listening. So I will share with the something and we will deploy it on the WhatsApp group. So thank you.
Thank you, sir.
See you next time. The slide, you can see it's not everything in the slide that you require. So when you go through the recordings, you can then jot down what you need to jot down, because this is the slide that I was scrolling through. So it's not everything in the slide that is required by you. And if you want me to teach everything in the slide, I will teach it. And your case becomes complicated. Is that what you want?
No.
I don't want that.
So you have to sit down quietly and have what is required. Thank you very much.
How about the link, sir? The link.
Thank you, sir.
It will be shared with the something.
All right.
It will be shared with